Let's talk about function continuity. What does it mean for a function to be continuous or discontinuous? Well, on the purely intuitive level, what you can think of as a function being continuous or discontinuous is fairly obvious, because essentially if you see a function that's just going like this and doesn't have any breaks or holes or gaps in it, then we can say that the function is continuous. And similarly, if you've got a function which goes kind of like this, for example, and then it continues from this point, then we can say that the function is not continuous or it is discontinuous because there is a gap here. So sometimes we're not interested in the entire function. Sometimes we're interested in, for example, a different regions of the function, or for example a specific point, and we want to find out if the function is continuous at this point. So now we can give a formal definition for whether a point, let's begin with points, whether a point is continuous or not. So let's make a definition. So a function f of x is continuous at a point x being equal to a if the following three conditions hold. So the first condition is that f of, sorry, that should be this color, f of a exists. So we need the point to exist, which means that if, for example, you have division by 0 at point a, then that's a problem. That makes the whole thing discontinuous. The second requirement is that the limit when approaching a exists. So the limit as x is approaching a of the function exists. So what this means is that when you approach from the left and you approach from the right, you should get the same value, which is not the case, for example, in this particular point, because here if you approach from the right you get this value of y, and if you approach from the left you get this value of y. Therefore the limit does not exist. And finally, the third condition is that this limit that we have up above, so the limit of the function with x going to a, is equal to f of a. So we really want the limit when we approach from the left and from the right to be equal to the actual function value. So what this means is that the limit is approaching the function from both sides, and it will give us the same result as if we just took the value a and plugged it into the function. So that's what we want. So let's take a look at an example. So for example, let's have a function that looks like this. Let me just draw it. So essentially we have, let's say, have a line going like this, and then we have a line going like this. So at point 2, for example, you can see that the function is continuous because the limits exist. If you approach from the left or from the right, you're going to get the same value. That's the value of the function. Therefore, everything is correct. However, if you look at this, let's say this is x equals to 6. So if you approach from the right, you get one value of y. If you approach from the left, you get a different value of y. Therefore, the limit does not exist, because the limit exists if the left and right limits are in fact identical. So now let's imagine that you have a function such as, for example, f of x equals 2x plus 7 divided by 4 minus x. So what can we say about this function? Is it continuous or not? At what point is the function not continuous? I'm sure you can guess that we have, since the first requirement here is that f of a should exist, we can plug in a value of x such that f of a would not really exist, and that value is x equals to 4. Because if it's x equals to 4, you get division by 0, which is undefined. It gives you infinity. Therefore, the function is discontinuous at x equals to 4. So now that we have a definition for continuity or discontinuity at a particular point, let's talk about the actual ranges So we might be interested in an interval and whether a function is continuous on an open interval. So for example, the definition, first of all, is that the function is continuous on an open interval from a to b if it is continuous on every point in a and b. So every point in this interval. So let's do another drawing. All right, so let's imagine that we have something like this and then something like this, and I'm going to give some values here. So let's say this is -2. Let's say this is 2. This is 4. And this is 6. All right, so this function is continuous on the interval from -2 to 2. But it is not continuous on an interval from 2 to 6. So this interval is not continuous because to be continuous on an interval, you have to be continuous at each and every point. And it's not continuous at the point where x is equal to 4. So finally, if we're interested whether or not the function itself is continuous, then simply instead of taking a and b, we take -infinity and infinity, and we say, well, is the function continuous at each and every point? So we have this idea of the function being everywhere continuous. Everywhere continuous. So the requirements for everywhere continuous is fairly obvious. You have every point which is actually continuous. So let's give some examples of everywhere continuous functions. So first of all, the power functions. Power functions. So if you have f of x equals x to the n, where n is positive and an integer, then this power function is continuous. So you can think of, for example, x squared, the function x squared, it's everywhere continuous. The second example is exponential functions. Exponential functions. So for example, something like f of x equals 2 to the x. So once again, that would be everywhere continuous. And then another example would be logarithmic functions. So typical example is f of x equals log base 2x, for example. So numerically, what the idea of continuity means is that small variations in the independent variable, meaning the variable that you have here, is gives you a small variation in the dependent variable. So that would be f of x or y or something to that effect.